Hello, my name is Adarsh Narayanan, and this is Lab 4 Oscillations. Introduction. The purpose of this lab is to investigate the motion of a spring mass system with the mass oscillating in an arc. Tracker. The software to track observed position. GlowScript. The computational model to predict/graph objects' motion and energy changes. Our goal. To determine whether the model follows the energy principle. And our result. The system's total energy remains constant at 0, thus demonstrating the energy principle. Our fundamental principles. Newton's second law. Systems change in momentum proportional to net force applied. You can see our F-net equations there. And then our energy principle. Systems change in energy is the sum of work done by surroundings and thermal energy exchanged with the surroundings. As you can see, the change in energy system equals the work surroundings plus Q. And in our system, we have to say, is mass, spring, and the earth. And our surroundings is nothing. Other useful equations. Update formula is derived from Newton's second law, so that includes the velocity update formula, the position update formula, the kinetic energy formula, the gravitational potential formula, and the spring potential formula. Our observed motion. So our object's mass is 0.402 kilograms, our string length is 0.7 meters, our initial position in the x direction is negative 0.107 meters, and our initial position in the y direction is negative 0.632 meters. Our initial velocity is 0 meters per second in all directions. And you saw our video showing the tracker software. Finding initial conditions. By using all the values in the table, we can solve for t, k, and the relaxed length. For t, we use the oscillation period, which is 2 pi times square root of m over k. And if we plug in all of our numbers, we get 1.5197 seconds. Solving for k. K is spring stiffness, so the formula for this is 4 pi squared times m over t squared, and then if you plug in all your numbers, you get 6.872 newtons per meter. And then we want to solve for relaxed length. And if you use this big equation here, you can slowly derive out of this and get just to an L naught. So our L naught is 0.1261 meters. Computational model initial conditions. By using all the values calculated on the last slide, we have to input this into our computational model. So you can see our mass of the ball, our position of the ball, and the velocity of the ball is the same as the values that we calculated in the last slide. We also have to make sure we point out our gravitational constant, which is 9.8, and our spring constant and relaxed length of the spring is also from our previous slide. Computational model, spring length, and system energy. So for our first 3 lines, we want to get our change in spring length. So that is mag L minus L naught. L is the first one, and then L hat is the second one. And then our next 4 lines are for the energy equations. So all of these equations are just the regular energy equations for each variable, but in computational GlowScript form. So we just want to input these formulas just so we can use it in our while loop later. So this is our while loop. So this is our computational model motion prediction loop. So first we want to make sure we talk about our time value just to make sure it's consistent with our tracker software. And then we want to define our initial energies and then calculate gravitational force using this. Then we want to calculate spring force on mass by spring by doing this, and then apply the momentum principle to update velocity and position. And then we want to do is update the spring, and using these 3 lines from the same lines in the previous slide, we can update the spring. And then finally, we want to calculate the energy changes, and this is done by using each energy formula and then subtracting it from the initial. So our computational versus observed model. So as you can see, it's very similar but not completely perfect. So that means there are some sources of error. Possible error number 1. In reality, the system is not isolated from the surroundings, so there will be work done from the surroundings. Possible error number 2. Inaccurate center of the mass placement on tracker. Is the energy principle satisfied? Almost. The energy principle is satisfied partially, but there are sources of error, which contribute to the reason why it's almost there. Since no external forces affect the isolated system, the change in energy must be 0. Even though different types of energies are in the system, the graph shows that the total change in energy is almost constantly 0. Comparing oscillation periods. In the x direction, we have that 3t equals 4.938 seconds, so we can get the original period, and then we use that period to get the stiffness, which is 5.858 newtons per meter, and then we do the same thing in the y direction, but we get a different number of stiffness, which is 6.872 newtons per meter. So, choosing different directions produces deviations in the period, which ultimately affects the spring constant in the graphs. Thank you for listening to my presentation. I hope you enjoyed.